In this session, we are going to go over a couple of practice problems that relate to distributions. And let's go over the first one. So the questions that we are going to go through, they are uploaded on module 1, on module 2 folder on Blackboard. They are practice problems of module 2. And we're going to go over those problems. So let's look at the first problem. The quality assurance department at a hospital, as one of the responsibilities that they have, they are looking at the correctness of medical records, and each one of the medical records has 95% chance to be correct. And suppose that an employee is going to begin checking medical records. And these medical records of different people are independent from each other. Each one of them has 95% chance of being correct. What is the probability that 7 of the first 10 medical records are correct? So the probability that in the first 10 medical records that we are going to inspect, 7 of them is correct. So what I want you guys to do when you look at these problems is that find out first what is number of experiments that has to be run, and then what is number of success. And also I want you guys to define what is success in your problem, because once you know success, you know what would be the correct value for the probability. So let's define success. What is the definition of success in this problem? We want to know the probability that out of the first 10 medical records that we are going to check, 7 of them are correct. So what is defined as success here?
Being correct.
Okay, the records being correct is success. What is P, which is the probability of success?
0.95.
0.95. What is the number of experiments here that are going to be run?
10.
10 of them. And what is the number of success that we want?
7.
So that's probability of, and 10 equals to 7. That means out of 10 records that we're going to check, we want 7 of them to be correct. And that's probability of correctness to the power of 7. And then 1 minus p, 0.05 to the power of 3. Okay. On average, part B. On average, how many of the first 4 records will be correct? So on average, if we check 40 records, how many of those will be correct on average? So number of experiments is, so again, we have to find number of experiments and number of success. So it says in part B, ask on average, how many of the 40 records, of the first 40 records that we are going to check will be correct? So what is the number of experiments here?
40.
So we are going to check 40 records, and we want to see on average how many of them will be success. Okay, so on average, mean, expected value, all of those means average. So average of number of success in 40 records that we are going to check. And success here means that they are correct. So the formula is NP, right? N is 40 here. And P, the chance of success is, which is correctness, is 0.95. So that number will be average number of records that will be correct in 40 files that we are going to check. Any questions so far? Let's go to question 2. In a clinical study, volunteers are tested for a gene, for a specific gene, and every person has 10% chance of having the gene. In part A, we want to know what if we test a total of 60 volunteers, what is the probability that 12 of them carry the gene? So we are going to specify number of experiments, number of success, and also define what is success in this problem. Okay, so in this problem, we are going to test 60 volunteers, and we want to know what is the probability that 12 of them have a specific gene. What is the definition of success here?
That the person carries the specific gene.
Yeah, carry the gene. And what is probability of success?
0.1.
0.1. We are going to test 60 people, and we want to see what is the probability that 12 of them have the gene. What is the number of experiments?
60.
And number of success?
12.
So the probability that among 60 people, 12 of them have the gene. That's selection of 12 out of 60. And probability of success is 0.1 to the power of 12 and 0.9 to the power of 48. Part B, how many persons that carry out the gene do you expect to be detected if 40 volunteers are tested?
4.
If we test 40 volunteers, number of experiments is 40. What is the average number of persons that we are going to find that carry the gene? So we want to find the average number of success. How many persons that will carry the gene do you expect to observe if we test 40 volunteers? Do you expect to observe? How many success do you expect to observe? So that's expected value or average or mean of the number of successes if we run the experiment 40 times or if we test 40 people. So that's expected value of the random variable n for d, meaning that we run the experiment 40 times or we test 40 people, and we want to know what is the average number of successes that we'll see in these 40 experiments. So the formula for expected value for binomial distribution is NP. N is 40 and P is 0.1. And the answer is 4. So if we test 40 people, on average, we expect to see 4 people that have the gene. Let's go to question 3. Consider that we have run a specific number of reactions.
Professor, can I ask a quick question?
Yeah.
So regarding binomial and Bernoulli, if we see a problem where it specifies success as 1 and failure as 0, but there's no number of trials, is that what distinguishes Bernoulli from binomial?
Exactly. So a binomial basically is repeating a Bernoulli so many times. Okay, so in the Bernoulli experiment, we just run the experiment only 1 time. Okay, so we run this experiment only 1 time. It leads either to the success with probability of P or to the failure with probability of 1 minus P. Okay, but how about the binomial? We repeat these Bernoulli experiments over and over and over. So the number of Bernoulli experiments that we run is the number of experiments. When we say we test 40 people, that means we have run the Bernoulli experiment 40 times. And each Bernoulli experiment is independent from the other. And each one of them independent from the other has the probability of P to be success and 1 minus P to be failure.
Okay, thank you.
What was the discrete uniform? Just very quick.
Discrete uniform?
That's when each outcome has the same probability.
So if, okay guys, I'll get back to question 3 in a second. So, but let me just explain discrete uniform in quickly, and then we go back. So let's say we throw a die, right? What are the possible values that you're going to say? 1, 2, 3, 4, 5, 6, right? These are possible values. What is the probability of each one of them? Probability of 1 is 1 over 6, 1 over 6, 2, 4, 3, 1 over 6, 1 over 6, 1 over 6, 1 over 6. Okay, so we can observe 6 possible values, and each one of them has the same probability to be observed. Okay, so in this scenario, we say that the number that we may see when we throw a die has actually uniform distributions because all these numbers have the same probability. Okay, so if I ask you, what is the probability that you observe 3 on a die, given the fact that you know your outcomes are 6 and all of them have similar chance, so the probability is just 1/6. I ask you, what is the probability that the number on the die is even? How many of these numbers that we observe on the die are even?
3.
2, 4,
1/2.
3/6.
1/2. Yeah, 3/6.
3 of them. So it's basically 1/6. Either it's 2 or 4 or 6. So that's 3/6. Okay. So whenever you have the results of your experiments or the random variable that you define gets some possible values, and all these possible values have the same probability of happening, that's uniform distribution. So let's say here, if you have 5 possible values, and all of them have the same probability of happening, so that's going to be 1/5, 1/5, 1/5, 1/5, 1/5. That's okay. So that becomes a uniform random variable. Okay, let's go back to question 3. So in question 3, we are going to actually run 200 reactions. Out of these 200 reactions, 48, so these are number of reactions. 48 of them lead to 6-degree temperature, 60 of them lead to 271 degree, and then 92 lead to 274 degree for the temperature. Okay, so this is what we know after running these reactions for 200 times. Now, I tell you, okay, this is what I know. This is what we have done in the past. This is what I know. Now I'm telling you, now I'm going to run 20 independent reactions. And I'm asking, what is the probability that exactly 12 reactions in results in the temperature less than 272? Okay, I'm going to run 20 independent reactions, and I want to find out what is the probability that 12 of them lead to a temperature that is less than 272. Okay, so we need to find number of experiments, we need to find number of success, and we need to find what is definition of success so that we can specify P. We run the experiments 20 times, we run these reactions 20 times, and I want to find out the probability that I observe 12 reactions in which the temperature is less than 272. So what is the definition of success here?
Less than 272.
The temperature is less than 272. What is the probability of success, or P, or the probability that a temperature, a reaction that we are running has a temperature less than 272? How we are going to get that?
108/200.
Okay, so we are going to basically use this historical data to find the probability of success. We know from the past that we have run this experiment or this reaction 200 times. Out of these 200 times, how many times the temperature was less than 272? 48 times and 60 times here. In both these categories, the temperature is less than 272. So what is the probability that when we run when we run this reaction, we observe a temperature less than 272? That means out of these 200, we have 48 plus 60. So that's the probability that when we run a reaction, we observe the temperature less than 272. And this P is going to be 54. Okay, so the probability of success is going to be 54.54 in this problem. Now, I'm telling you in part A, we are going to run 20 independent reactions, and I want to know What is the probability that number of success is 20? What is the number of experiments?
20.
And what is the number of success that I'm looking for?
12.
12. So the probability that and
20 choose 12.
exactly choose 12 out of 20. The probability of success, which is 54 to the power of 12. The probability of failure, which will be 46 to the power of part. Next part, I mean, it's called part C. It should be part B, but anyway. Next part.
Professor, so is the probability that you calculated, the p is equal to 0.54, is that considered an independent probability?
Independent of probability of success. So all the reactions here, and then when we run these 200 reactions initially, these are independent experiments, independent.
Okay.
48 of them led to this, 60 led to this, and 92 led to this. So
Okay.
if you want to find a probability that, okay, if I'm going to just randomly run one more experiment, what is the probability that the temperature is less than 272? So we just look at historical data. In the past, we have run 200, and 8 of them are the ones that led to less than 272.
Okay, thank you.
So let's look at next problem. What is the probability that, again, we are checking and we are running 20 independent reactions. That's fixed. We are running 20 independent reactions. We want to know what is the probability that at least 18 reactions result in a temperature less than 272, which is defined as success here. So again, number of experiments is 20. We run the reactions 20 times. We want to know the probability that number of success is at least 18. Okay, so that's what we want to know. So that means probability that out of these 20 experiments, we have at least 18 success, at least greater than or equal to 18. Is that correct? So the number of success is greater than or equal to 18. That means at least we have 18 success in these 20 experiments. Do you guys agree? Does that make sense?
Yes.
Yeah, that makes sense.
So that's probability of N20 equals to 18. So that's equals to number of success equals to 18, or probability of N20 equals to 19, or N20 equals to 20. So when I say or, that's why I add these probabilities together. So just calculate each one of these probabilities and add them together. For example, let me calculate this one. So out of these 20 experiments we have run, 20 reactions, what is the probability that 19 of them are success? So that's 19 out of 20, 0.54 to the power of 19, and 0.46 to the power of 1. So that's probability of N20 equals to 19. So do the similar calculations for this probability and add them together. That gives you the probability of observing at least 18 success. If I tell you what is the probability that out of these 20 reactions that we have done, I observe at most 2 success. How do you write that? Out of these 20 experiments that we have run, 20 reactions that we have run, what is the probability that we observe at most 2 success?
It'd be P of N20 is less than or equal to 2?
At most, yes, is less than or equal to 2. So 2 is the maximum, at most 2. So that's probability of N20 equals to 0 plus probability of N20 equals to 1 plus probability of N20 equals to. What is the expected number of reactions that result in a final temperature of less than 272? So again, we run the 20 reactions. What is the expected number of reactions that lead to the desired temperature? Again, number of experiments is 20. And the question is asking, what is the expected number of reactions that result in the desired temperature? What is the question wants from us?
The mean.
What is the expected number, the average, the mean of reactions that lead to success? So that's expected value of this random variable. And that's NP. N is 20. And P, the probability of success, is 0.54. You guys are okay? Let's go to question 4. Each multiple choice question on an exam has 4 choices. Suppose that there are 10 questions and the choice is selected randomly and independent from the other questions. So let X denotes the number of questions that have been answered correctly. What is the type of the random variable X? So we have these multiple choice question. We are going to answer each question randomly. So that means we are going to pick one of these 4 answers randomly. And we have 10 questions, and random variable X shows the number of questions. If we answer these 10 questions, random variable X shows the number of questions that we will answer correctly. So I want to know what is the type of this random variable. Do you guys know that?
10.
We have 10 questions. And then we want to define also the number of success and also define first what is success. What is success in this experiment? We have 10 questions, and I define my random variable as number of questions that I have answered correctly. What is success? Okay. So we want to see what is the probability that 5 of those 10 questions are correct. So the number of success is 10, and we want to find the probability that the number of success is 5, and we set the number of success is correct answer. And the probability of giving a correct answer is 0.25 because it's multiple choice question, and you have 25% chance to, if we answer randomly, we have 95% chance to answer the question correctly. So what is the probability that n of 10, we answer 5 questions correctly? So 5 out of these 10 questions are going to be answered correctly with probability of 0.25, and the rest are going to be answered wrongly with probability of 0.75. Part C is asking, what is the probability that the student answers fewer than 5 questions correctly? So we still have 10 questions. Still the number of experiments is 10. We want to see what is the probability that the student answers fewer than, less than 5 questions correctly. So probability of n, 10, less than 5. So basically that means probability of n, 10 equals to 0 plus equals to 1. So the values is 0, 1, 2, 3, 4. So we have to find the probability for each one of them and add them together. So probability of n10 equals to 0, probability of n10 equals to 1 plus n10 equals to 0.
Professor, probability of n10 equal 1, n10 equal 2, all the way to n10 equal 10. When you add them, you have to be 1 or no?
Yeah. So that's basically definition of probability mass functions, right? In probability mass functions, we always say, let's say f of x of x, or the probability that x equals to lowercase x. Always you have a bunch of value for x. So I'm just making up here. So let's say 0, 1, 2, I don't know, 10, 12. So let's assume these are your possible values for x. And in these probability mass functions, we want to know the probability associated with each one of these possible values. And at the end, the sum of these probabilities should be 1, meaning that at any point of time, one of these values should be correct. This is your random variable, right? So at any point of time, one of them should happen. So I don't know which one exactly. Obviously, it depends on the probabilities. If one has higher probability, that has higher chance to be happening. But in any case, the sum of these probabilities that you calculate for each one of the possible values of this random variable equals to 1. Question 5. An electronic product contains 4D integrated circuits. The probability that any circuit is defective is 0.1, and the integrated circuits are independent from each other. The product operates only if there are no defective integrated circuits. What is the probability that the product operates? Okay. So the probability that the product operates means, so now, in this question, let's look at what is number of experiments, what is number of success, and what is definition of success in the first place. So we have 4D circuits that are independent from each other, and each one of them can be defective with probability of 1%. And I want to know what is the probability that I have no defective circuits. So what is success here?
Wouldn't it be defective circuits?
Well, in this case, wouldn't it be all
Non-defected.
no defective? All 40 have to function.
Yeah, all of them.
As circuit being defective, it really doesn't matter. Any one of them is correct. We can do both approach. Defective circuit. What is the probability of success?
0.01?
0.01. So if you define success as defective circuit, the probability of that happening is 0.01. And I want to find the probability that the product operates. That means probability of no defective circuits. So the number of experiments is 4D because I have 4D of the circuits, and I want to know what is the probability of success, meaning having defective circuits is 0. So I want to find no defective circuits, meaning that no success. So the probability of success is going to be 0. So that's probability of N4D equals to 0. So because I want to find probability of product operates, that means no defective circuits. So if my success is a part being defective, then the probability of no defective success, meaning no success. So the number of success is 0. And that's going to be, so the probability that the product operates means that all of them are working. None of them are defective, which makes sense also. If I wanted to write it, that means the first circuit is working and the second circuit is working and the third circuit is working all the way to, and the 40th circuit is working. The probability of first one is working is 0.99 and second one is working 0.99 and third one is working 0.99 all the way to 40th working 0.99.
But this was my question earlier, like when I asked, like we have to test like the first one, the second and the third, and in this case we're all just assuming all 40 are working.
Yeah, so
in one step.
Yeah, so all you have to understand is that in these type of problems, binomial or Bernoulli, we are looking at independent experiments. Okay, so if I want to find out what is the probability that 4D of them are working, that means, so the first one, I have to look at the first one and the second one and the third one and the fourth one and so forth. Okay, So, and this is exactly what is happening. I look at all of these and the number between, so, and then I have to use and between them. So that's why here, if I calculate this, is 0.999 to the power of 40. And that's what we get here. Because 0 out of 40, what is this number, guys?
1.
Yeah. This number is 1.
Is 40 factorial over 4? Yeah, 1.
1. What is this second part?
1.
Is 1.
And so this is the only part that is left.
Mm-hmm.
What is this part? Let me see.
Oh, yeah. So I noticed what happens is you can flip this whole thing around. I think this, I don't know if this works generally, but you could just put P as 0.99 and then do N40 equals 40.
Yeah.
Yeah.
So we could let's look at this in a different way. So here in the second way, I'm going to define success as circuit not defective. Okay, that's the definition of success. Here I said circuit defective is success. Here I said circuit not defective is success. What is the probability of success here?
1 minus 0, 0.09, 99.
Okay, so that's the probability of success. Now let's look at this probability here. The probability that the product works means no defective or all of them are good. Okay, so when I say no defective, it means probability that all are working correctly. Okay, so if I want to write that, so that's probability of
N40 to
equals to 40. That means all of them are working correctly. So that means 40 out of 40. Probability of success, which is 0.99 to the power of 40. Probability of failure. So if I define success, my random variable, if I define it as circuits not defective, then probability of that the product is working means I have to observe 4D success. For the product to work, I have to observe 4D success. If I observe 4D success means 4D of this. 4D circuits not defective. And 46 is the probability of not defective is this. So let's go to module 2, part 1, and open the homework, which is the first homework I gave you guys for this module. We are looking at question 6. So in question 6, it says, we consider circuits. So in this circuits, it has 2 parts, part 1 and part 2. Part 1 is working with probability of 0.7 and part 2 is working with probability of 0.76. We define a random variable x as number of devices or parts that have failed. Okay, so this is important. And we want to write down the probability mass function. So the first thing I have to find out is that what are the possible values for the random variable x? Can you tell me? What are the possible values? The random variable x shows number of devices that have failed. We have 2 devices, P1 and P2. Number of devices that have failed. What are the possible values for this random variable?
0, 1, and 2.
0, 1, and 2. If I want to write down the probability mass function of this random variable, I have to find the probability that x equals to 0, x equals to 1, and x equals to 2, and just write them here. So let's consider each one. So what is the probability of x equals to 0? Which means number of devices that have failed is 0. What is the probability that number of devices that have failed is 0? What does that mean?
That they all worked.
Yeah, so when I say probability of x equals to 0, that's
0.7 plus 0.76.
So what I want to find out here, what is probability of x equals to 0? That means what is probability that number of devices that have failed is 0. 0, that means nothing has failed. The first one is working. and the second one is working too.
I usually confusing why sometimes we do multiplication and sometimes we do plus for.
So because I say, what is the probability that number of devices that have failed is 0? What is the probability that none of these have failed? So what do you say? Just in sentence, forget about probability.
Oh, okay.
It's when the first
both of them is working, so.
The first one is working and
yes,
the second one is working. So that's just simple probability, simple multiplication.
Okay.
So for the next questions, you will see we have the orange. So in the next one, we want to see what is the probability that x equals to 1. What does that mean? Number of devices that have failed equals to 1. Just forget about probability. Just tell me when would that happen? When number of devices that have failed equals
one of them is failed.
Okay.
P1 or P2.
So when P1 has failed and P2 is and P2 is working, or
P1 is working and
P2 has failed, right? So when scenario 1 happens or scenario 2 happens. So what is the probability that scenario 1 happens? P1 has stopped working and P2 is working.
So
P1 is not working. We know the probability of P1 working is 0.7. P1 is not working.
0.
0.3.
1 minus P. Yeah, you're right.
So P1 is not working and
multiplication by 0.76.
P2 is working. Or
and
so the scenario 1 happens or
plus
scenario 2 happens. And scenario 2 is when P1 is working, 0.7, right? And P2 is not working. Probability of
1 minus P2.
0.24. So that's probability of scenario 2. So when scenario 1 happens or scenario 2 happens, that probability is going to be 39.6. Okay. And now what is the probability that x equals to 2? Let's do. So what is the probability of x equals to 2? Number of devices that have failed equals to 2. That's when the first one fails and the second one fails. So do you want me to solve the last question too? Question 12, which is similar. Okay, okay, so we have this circuit still is the same. 2 parts, P1 and P2, and P1 is working with probability of 0.7, P2 is working with probability of 0.76. However, the definition of random variable here is different. X shows the number of devices that have not failed. This is different from the previous one. The previous one, X shows number of devices that have failed. You see here? But here, now X shows number of devices that have not failed. Okay, what are the possible values for X? The number of devices that have not failed. Possible values.
0, 1, and 2.
0, 1, and 2. And although the question wants the f of x1, which is a cumulative probability, and that means probability of x equals to 0 plus probability of x equals to 1, right? So we have to find these two probability to be able to answer the question. So let's go and find the probability mass function. F of x equals to 0, 1, or 2. What is probability of x equals to 0? X equals to 0 means number of devices that have not failed equals to 0. What does that mean? When would that happen? Number of devices that have not failed equals to 0. Can you say it in a different way?
All of them worked.
All of them are what?
Working?
No. Number of devices that have not failed is 0. That have not failed. If number of devices that have not failed is 0, that means both of them are working?
Yeah, in this one, I
No.
just took the opposite of the first solution and went from there.
So the number of devices that have not failed is 0, which means the first one has failed and the second
It
one.
means that, yeah, they all failed.
Okay, so if the number of devices that have not failed is 0, which means both of them have failed. Okay, probability of 0.3 multiplied by 0.24. Okay, that's 0.72. What is probability of x equals to 1? Which means number of devices that have not failed is 1. So that means one of them has failed and one of them has not failed. Okay, again, two scenarios. If the first one has not failed and the second one has failed, that's that. Or the first one has failed and the second one has not failed. And then for this probability, to calculate this cumulative probability that we want, we just have to add this probability of x equals to 0 to probability of x equals to 1. The only thing for this question was that it's just the definition of x was a little confusing.
So for this, for that part where we do, where one succeeds and the other one fails, and we add the two scenarios, would I be able to ask you for like the generic formula for that?
For the x1, basically?
Yeah, for the scenario in which one fails and the other one succeeds, and then...
So I would say in those scenarios, just think about, like, this is a simple scenario. So just think about, I can't tell you a general formula, but just in this problem, when x equals to 1, means number of devices that have not failed equals to 1. So have not failed is 1. So that's one possible scenario is when P1 has not failed, however, P2 has failed. So that's one scenario. That's scenario 1, when one of the devices has not failed. What is the other scenario? It's the scenario when P2 has failed, however, P2 has not failed, however, P1 has failed. So in scenario 2 as well, we have one device that has not failed. Okay, so the probability of x equals to 1, meaning one device has not failed, happens when scenario 1 happens or scenario 2 happens. So just add the probability of these two scenarios. So pretty much there's no general formula, but I would say try to understand the definition of random variable. And if you know the definition of random variable, if you know if you can define the possible values correctly, so for each probability, just go back to the problem and just see what it means. Just say it in sentences. And once you understand that, then it's easy to calculate the probability because you have all the numbers in the problem statement. Just try to understand what it means for x to be 0, what it means for x to be 1, or for x to be 2. And then use those numbers to calculate the probability.
Okay, thank you. Yeah, I just didn't know to actually take like the 0.7 and multiply it to the 0.24, but now it makes more sense. Thank you.
The scenario 1 means first one is working and second one is not working, and means multiplication. Scenario 2 means first one is not working and the second one is working, and means multiplication. When I say scenario 1 happens or scenario 2 happens, or means plus. And that's why here we have plus for the ors, and here we have multiplications for the ands.
Professor, could you quickly go over question 1 on the homework?
The one that says a die has the number 1 through 6?
Yes, yes.
A die has number 1 through 6 on each side. When it's rolled, the likelihood of the die lands on any one of the 6 sides is equal. Let x be the random variable that takes value 0 if the die lands on the side of an odd number, and 1 when the die lands on the side that has even number. Determine the mean of x. So what is the definition? Okay, so x is a random variable, and it's going to take 2 values. It tells the random variable takes value of 0 if the die lands on the an odd number, and it's going to take value of 1 if the die lands on the even number. So we know the possible values is 0 or 1. Those are given. What we have to find out is the probability of each one of them. Probability that x equals to 0 and probability that x equals to 1. Because the question asks for the mean of x. If I want to calculate expected value of x or average of x, I have to multiply its value by the probability and then add to it the other value multiplied by its probability, right? That's just the definition of average of a random variable. Multiply each one of the values by the corresponding probability and just add them together. Okay, so I need to find these probabilities. Obviously, the probability of the first one multiplied by 0, we don't have to, but just here for the sake of learning, we are going to find these 2 probabilities. So, okay, so the experiment is that we roll a die. Any one of the 6 numbers can be shown, and if we see odd numbers, that's x equals to 0. So the question is that what is the chance that x equals to 0, or what is the probability that when we roll a die, we observe odd number. Okay, so when we roll a die, how many number potentially we can observe? What are the possible options?
1, 2, 3, 4, 5, 6.
There are 6 of them. How many of them are odd?
1, 3, and 5.
3 of those. Okay, so the probability that x equals to 0, or when we roll a die, we observe an odd number, is 3 out of those 6 possible outcomes, and that's 1/2. And probability of x equals to 1, I can calculate probability of x equals to 1 in 2 ways. One way is to just look at the definition of probability. So x equals to 1 if you observe even numbers when we roll a die. So first tell me what are the possible number of numbers that we can observe when we roll a die. It's 6, right? How many of those are even numbers? 2, 4, and 6. So 3 of them are even numbers. So the probability of x equals to 1, or observing even numbers when we roll a die, is 1/2. Okay? However, I could calculate this probability in a different way as well. What is the other way, guys? Which is simpler, a lot simpler.
You can find 1 plus or a plus b over 2.
No, so that comes from the definition of probability mass function. So remember, f of x can get 2 possible values, 0 and 1. We calculate the probability of 0, which is 1/2. What was the definition? One characteristic of probability mass functions.
1 minus the other.
The sum of these 2 probabilities is 1. So if I have one of them, The second one is just 1 minus 1 over 2, which is 1 over 2. So here it was easy to find the second probability, but sometimes it may just needs a lot of work to find the other probabilities. So if there are just two numbers, just calculate 1 minus 2. So even if there were 3, maybe we had also probability of x equals to 2. If you find 2 of them, if you have 2 of them, just do 1 minus the sum of the other 2 and find the probability of the third one. So you don't need to do the calculations for each one of them separately, especially if the calculations are very time consuming.
It's okay to go to the quiz now, or we still homework right now?
No, and we can go anywhere that you guys want.
Yeah, for the quiz, just the most day. I don't know what means the word most instead of exactly. So that's why my weakness.
No worries. That's the second quiz.
Yeah, the second quiz and the question is 5, I think.
5. Okay. A particular traffic light on your morning commute is green 20% of the times. Assume that each morning represents an independent day. Over 5 mornings, what is the probability that the light is green at most one day? Okay.
So it's 1 or less.
So yeah, let's look at this. So first of all, over 5 mornings. So it means number of experiments, or that these 5 independent experiments is 5. We look at over 5 days. What is the probability that the light is green at most one day? So the success, the definition of success here is the light being green, and the probability of success is what is it? It's 0.20, 0.2, right? That's the probability that the light is green. Now we want to find out the number of success. So the number of success is when the light is green. So we want to find the probability that the number of days that the light is green is at most 1. So the probability of this random variable that I'm going to write it as n5 is at most 1. At most 1. Can it be 2?
No.
Okay.
Yes.
At most. So this part is English. Okay. And I know my second language is English too, but this part is just pure English. So I want the number of days of these 5 days, number of days that I observed green is at most 1. Can I say 4 is included? At most 1.
Because we say 5 in the beginning, yeah.
Is
including, 5 is including.
Okay, but that's total number of experiments. So okay, let's look at this. Let's assume that you have $5.
Okay.
And I tell you, give me at most $2.
Mm-hmm.
At most $2. Do you need the possibility of you giving me $4? Is that included in the sentence that I said? I tell you.
No.
Okay.
No.
Okay. So the same concept is here. So we have 5 days. These days are independent. That's similar to the $5 that you have. And I say, what is the probability that at most one day is green? So is the 4 days being green included?
No.
No, at most 1. At most 1. That means 0 or 1. Nothing more.
Oh, okay.
So that n5 is less than or equal to 1. Probability of n5 equals to 0 plus probability of n5 equals to 1.
Thank you, Professor. That's help.
So at most, at least, so if I tell you, for example, what is the probability of at least 3 days of seeing green light? How do you write? What is the probability that at least you say
That means at least this means above of it, the
Exactly.
number.
Exactly. At least 3 days. So if I
So that's be 4, 5,
exactly,
and 3.
if you see 4 days, that's included in the at least, right? So that's probability of n equals to 3 and 4.
Okay, I got it. Exactly. That means just 1 day. Okay. Thank you.
Yeah, exactly means exactly that number.
Okay. So this problem is in the English words.
I know there's no matter. I have been there, so that's why I'm telling you.
Thank you, though.